Hi everybody, in this video we are going to talk about equilibrium constants. But before we do that, I want to connect Unit 9, which was a unit about rates, to this unit, Unit 10. So how do rates relate to equilibrium constants? Now, this idea only works if you are looking at an elementary step, so just take a note of that. And let's take a look at this reaction, the conversion of N2O4 to 2NO2, and these double arrows are known as equilibrium arrows, and they tell you that the reaction is at equilibrium. In equilibrium, the forward and backward reactions are equal in terms of rate. In other words, the system is at dynamic equilibrium, or in other words, things are happening, which is why it's called dynamic, but they cancel each other out, which is why it's called equilibrium. So in the end, we have a dynamic equilibrium, but regardless, nothing is happening overall. So we have this reaction, and let me tell you a little secret about this reaction. For our purposes, this net reaction happens in one step. So the net reaction is the elementary step. So we can use the coefficients as orders, since this is directly from Unit 9, where by looking at elementary steps, we can determine the rate law. And since this is an elementary step, then we can determine the rate laws for the forward and backward reactions. So for the forward reaction, we have Kf, which is the rate constant of the forward reaction, times the concentration of N2O4 to the first power, since there's a coefficient of 1 there. And this is equal to the rate constant of the backwards reaction, and this is multiplied by the concentration of NO2 squared, because it has a coefficient of 2. So, doing the math, we can move things around, and we can get that Kf over Kb is equal to the concentration of NO2 squared over the concentration of N2O4. And when you combine these two Ks into one K, it is called the equilibrium constant. So, for net reactions that happen in one step, or in other words, the net reaction is the elementary step, then we could find a relationship between the equilibrium constant and the rate constant. And it turns out that these are equal to the concentration of the products with the appropriate coefficients over the concentration of reactants. So, in the end, KEQ is equal to the concentration of the products over the concentration of the reactants, but of course we have to include the orders for the exponents. Now, the thing about this is that for elementary steps, or for reactions involving only one elementary step, the forward rate constant divided by the backward rate constant is equal to KEQ, a constant that describes the ratio of products to reactants at equilibrium. So remember, this is only for elementary steps. Now, if you have a net reaction that does not consist of one elementary step, then you cannot relate the rates of the forward and backward reaction to the equilibrium constant. And you might be able to, but it's definitely more complicated than saying that Kf over Kb is equal to Keq. So for most purposes, assume that the Kf over Kb is not equal to Keq, unless you are told that the net reaction consists of only one elementary step, and in that case, the elementary step is the net reaction. So all in all, this relationship between KEQ and the rate constant is for a very niche situation where the elementary step is the net reaction. So for most purposes, since most reactions are multi-step, or they consist of many elementary steps, then we typically do not assume this. So let's move on and talk about how we can write the equilibrium expression for the equilibrium constant without having to rely on rates. So, what's cool is that you could very easily write the equilibrium constant by putting the products over reactants with their respective coefficients as the powers. So, note that in your equilibrium expression, you should have gases and aqueous solutions only. So anything that's not a gas or an aqueous substance will not be part of the equilibrium expression, and I will explain why later. But basically, this reaction involves a gas and an aqueous solution reacting to form an aqueous solution and another gas. So, to write equilibrium expressions, we put products over reactants. So, we have to note that the gases are in atmospheres and they're written as partial pressures, and our aqueous solutions are written in terms of concentration and more specifically in molarity. So, for our products, we could start with C, and we see that C has an aqueous symbol, which means that it will have a concentration. So the concentration of C and the coefficient will be the exponent, so concentration of C to the C times, now what is this? Well, this is going to be the partial pressure of D, since D is shown to be a gas, and this lowercase d becomes the exponent. Now what about our reactants? Well, we could start off with A, and since A is a gas, we are going to write it in terms of partial pressure. So the partial pressure of A to the A power times the concentration of B, since B is aqueous, to the B power. Now we have to be careful about our notation. So partial pressures are always in parentheses, and concentrations are always in brackets. And notice how they're being multiplied and not added in the equilibrium expression. So products over reactants and their respective powers put on top. So now that we got that, let's write an equilibrium expression for this reaction over here, which involves two gases. So it's going to be products over reactants, and since they're both gases, then we will put them as partial pressures. So the partial pressure of NO2 squared, since the coefficient is 2, over the reactants, which is the partial pressure of N2O4, and the coefficient is 1, so it's to the first power, or you could just not write that at all, is equal to K. Now, why is it called Kp? Well, if all substances are gases, there is a special type of K you can use. So you don't simply have to write K or KEQ. These are not very specific. Instead, you can write Kp, which basically tells you that everything here will be gases. So the P is pressure, and this is an equilibrium constant, assuming that all the substances in your equilibrium expression are gases. So, now that we're done with that, let's talk about why we don't include solids or liquids in our equilibrium expression. So in reality, the equilibrium expression employs an idea called an activity. The activity is defined as the concentration or partial pressure or density or anything divided by the standard state conditions of that substance. So, the standard concentration of an aqueous solution is always 1 molar, and the standard pressure is always 1 atmosphere. Now, we can write this as an equation, so activity is equal to any condition divided by standard conditions. So, for example, the activity of 5 molar hydrochloric acid is 5 molar, or the any condition part, over the standard condition, which for a solution is always 1 molar. So 5 molar divided by 1 molar is actually 5, and that's the activity of 5 molar HCl. What is the activity of 3 atm NO2 gas? Well, 3 atm is our any condition, and our standard conditions are always 1 atm for pressure. So 3 atm divided by 1 atm is going to be 3, and that's our activity. So, why am I talking about this? Well, if you remember from the previous slide, I told you that you have to put your pressures in atmospheres, and your concentrations in molarity. And why is that? Well, it's because the concentration of HCl in molarity is numerically equal to its activity. So if I had the concentration of HCl here to the second power, let's just say, you could plug in your molarity of HCl, or 5, and it would spit out an answer that is identical to if you plugged in the activity, since the activity is equal to the molarity of the HCl, as you can see right here. So either way, if you plug in 5 as the activity, or if you plug in 5 molarity, they will both be numerically the same, which is why you are allowed to plug in the concentration of solutions into the equilibrium constant, even though you're actually supposed to use something called the activity to do it. But since activity and concentration are the same, then you could plug in either one and you'll get the same numerical answer. Now, what about pressure? Well, the partial pressure of a gas like NO2 is equal to its activity. So when you plug it into the equilibrium expression, you're actually supposed to plug in the activity into the equilibrium expression. And we know that the activity of NO2 gas is 3. But the thing is that the pressure in atmospheres for NO2 gas is also 3. So either way, if you plug in the activity of NO2 or the pressure of NO2 in atmospheres to the equilibrium expression, you still get the same number, which is why you are allowed to plug in pressures into the equilibrium expression as long as it is in atmospheres. So the cold hard truth is that the equilibrium expression is not based on concentrations or pressures. It is actually based on the activity of the substances. So let A equal the activity. So the equilibrium expression for this, no matter what state you have, will always be the activity of C to the C power times the activity of D to the D power over the activity of A to the A power times the activity of B to the B power. And this is all based on the reaction. So equilibrium expressions are actually based on a concept known as activities, but since the activity is equal to molarity and pressure in atmospheres, then you could instead plug in molarity and atmospheres into the equilibrium expression instead of the activity, and that's much easier to do. But before we continue, let's talk about why we can't plug in solids or liquids. Well, we can consider the concentrations of solids and liquids in terms of density for the most part. The standard condition for the density of ice, which is a solid, is going to be 0.917 grams per milliliter, because normally, under standard conditions, the density of ice is this. Now, if you remember from enthalpy, the standard conditions is that little degree sign there, or that not sign, and this means 1 atm, 1 molar for all solutions, and last but not least, 25 degrees Celsius, typically, but this can vary. So under these conditions, it turns out that the density of ice at standard conditions is this. Now, what is the density of ice when it's involved in a reaction? Well, unlike solutions and gases, no matter how much ice you have, the density of ice will always stay the same. So therefore, the density of ice will stay the same, and that means that the activity for ice and other solids and liquids as well is going to be 1, because the density does not deviate from the standard conditions no matter how much ice you have. So you see that the activity of solids and liquids tends to be 1, and anything multiplied by 1 gives the same answer. So we exclude liquids or solid substances from our equilibrium expression since they have an activity of 1, and if you multiply them, you get the same answer, so that's why we don't include them at all. So over here, this is the true equation for the equilibrium expression K. But we can substitute these for more simpler things that are easier to find. So, since the activities of solids and liquids are 1, we can ignore them in the equilibrium expression. The activities of gases are equal to their partial pressures in atmospheres, and the activity of aqueous solutions are equal to their concentrations in molarity. So, essentially, you can turn the activity of C, which is a gas, into the partial pressure of C to the C, and you can multiply that by the activity of D to the D, which is actually the concentration of D to the D, since these two are numerically the same, since activity is equal to concentration in molarity. Now, what about our solids and liquids? Well, the activities of solids and liquids are going to be 1, so we chug in 1 to AA and AB, and we know that anything to the 1 is going to be 1, so they essentially just disappear, and in the end, the equilibrium constant for this reaction up here is going to be the partial pressure of C to the C power times the concentration of D to the D power. And note your units, so this is ATMs, and this is molarity. And let's go back and talk about one exception. So there are actually a few, but I'm going to talk about one. So sometimes liquids can be included in the equilibrium expression. Why is that? Well, H2O can be considered to have a standard concentration, or the concentration at 1 atmosphere and 25 degrees Celsius. So the 1 molar does not apply because water is not a solution, it's the solvent itself, so we don't consider that 1 molar in this case as our standard concentration. So the standard concentration for water, which is not a solution, so we don't use 1, is related to its density. So 1 gram per ml can be changed to 1,000 grams per liter by multiplying the top and bottom by 1,000, and using the molar mass of water, we can find the molarity of water, and we see that the molarity of water is 55.5 molar. Under dilute conditions, the concentration of water remains constant, so the M of water will be around 55.5 molar most of the time. Since 55.5 molar divided by 55.5 molar is 1, water is excluded from the equilibrium constant. But if we have a concentrated aqueous solution, let's just say that we had 1,000 grams of water dissolving a lot of sugar, and normally the volume is supposed to be 1 liter as shown by the density, but this time the volume turns out to be 1.10 liters, probably because the sugar takes up space too. Now, our new concentration of water is 1,000 grams divided by 1.10 liters of solution, multiplied by the molar mass, and we get 50.4 molar for the concentration of water. So our concentration of water isn't equal to the standard conditions anymore. So we have to calculate the activity of water now. 50.4 divided by 55.5 is 0.909. So in this case, especially for concentrated aqueous solutions, we have to include liquid water in our K expression, and its value will be 9.09 to the whatever power, depending on the coefficient. But almost all the time, we ignore water in our K since its concentration only really changes when a lot of solute is dissolved inside it, or in other words, there is a concentrated aqueous solution. So use the activity of water if you are dealing with concentrated solutions, or if you want, just don't do it at all, because this is just done for precision, and if you like to be precise, then go ahead and do this. So as you can see, by not doing activities, but instead by focusing on partial pressures of gases and the concentration of aqueous solutions, we can more easily find the equilibrium expression by just looking at those, and of course, ignoring solids and liquids as they are equal to 1 for their activities most of the time. So by focusing on gases and aqueous solutions, it really cuts the time it takes to do this process, and it's a much more simplified version. So now let's talk about something called Le Chatelier's principle. Now this principle tells us that doing things to a reaction at equilibrium, and this is important, you are starting at equilibrium, so you're starting at when nothing is happening, and doing things to a system at equilibrium can cause the rate of the forward reaction to be greater than the rate of the backward reaction. The converse, or the opposite, can happen as well. This process can cause the reaction to go forwards or backwards overall to restore equilibrium. So, we know that at equilibrium, the forward and backward rates are the same. Substances don't change in concentration at equilibrium, since the forward and backward rates are canceling each other out. Now, as you can see, there's a big wall of text that we are going to read, but let's get to it. So, Increasing the concentration or pressure of a reactant found in the equilibrium expression shifts the reaction forward. And remember, the net reaction is going forward because now the forward rate is greater than the backward rate. And this occurs because the reaction is working hard to remove these excess reactants. This causes the reaction to go forwards overall, as I just said. Note that adding solids, liquids, or anything not found in the equilibrium expression will not disturb the equilibrium unless it is somehow impacting the concentration or pressure of the reactants, such as adding water, a liquid, to dilute an aqueous solution involved in a reaction. In that case, that would decrease the concentration. So, doing the opposite, or in other words, the opposite of this, or decreasing concentration / the pressure of a reactant, will cause the opposite to happen. Now, what if we focus on the products? Increasing the concentration or pressure of the products found in the equilibrium expression shifts the reaction backwards. So in this case, the forward reaction will be slower than the backward reaction now, because the reaction is working hard to remove these excess products. So that's why overall the reaction wants to go backwards to remove these excess products. And remember, it is doing this to restore equilibrium. Now, the same note as above about adding solids, liquids, or anything not found in the K expression applies to the products as well. Now, doing the opposite of increasing the concentration / pressure of a product will cause the opposite to happen. So if you decrease the concentration or pressure of a product, then the reaction will go forwards instead of backwards. Now, what about increasing the temperature of an endothermic reaction? Well, since heat is on the left side and it's being consumed, increasing the heat or the temperature of an endothermic reaction will push the reaction to the right to remove the excess heat. But this time, the equilibrium constant, as well as the rates of the forward and backward reactions, will change. So, increasing the temperature favors the products, so the equilibrium constant will increase. And remember, the equilibrium expression is products over reactants. So if it favors products, it will increase the numerator, and this will cause a bigger equilibrium constant since there's a higher product to reactant ratio. Now, increasing temperature, as we know from Unit 9, increases both the forward and backward rates, since increasing temperature will increase the rate of literally anything involving chemicals. But the forward rate increases more than the backward rate, and because of this, since the F rate is greater than the B rate, then the reaction moves forward. Now, decreasing the temperature will do the opposite for an endothermic reaction. So think about what happens there. Increasing the temperature of an exothermic reaction, where heat is on the right side and being produced, will shift the reaction to the left to remove excess heat. The equilibrium constant will favor reactants, so the equilibrium constant decreases to favor reactants, and if you remember, products over reactants is equal to K, and increasing reactants down here lowers the K. The net reaction will go backwards overall because, as we know, increasing temperature will always increase the rate of the forward and backward reaction. It's just that the backward rate will increase more than the forward rate, so in the end, the backward rate is faster than the forward rate when you increase the T of an exothermic reaction. Now, decreasing the temperature of an exothermic reaction will do exactly the opposite. So think about what happens there. So now let's talk about the next point. Increasing the pressure of a system or decreasing the volume of a system, and they do the exact same thing, by the way. So doing either of these two to a system. So, for example, if you're increasing the pressure of a system, you're increasing the pressure of all the gases, not just one gas, but all the gases. And if you're decreasing the volume, you're decreasing the volume for everything. So doing this favors the side with less moles of gas, since producing less moles of gas will relieve the gas pressure and decrease the pressure. Now, let me show you how that works. We know PV is equal to nRT, and lowering N will lower the P at a constant volume and temperature. So that's why by decreasing the moles of gas, by shifting to a side with less moles of gas, we actually are decreasing the pressure and relieving the extra pressure that we put. Now, doing the exact opposite, or decreasing the pressure or increasing the volume, since they do the same thing, will cause the opposite to happen, of course. Now, if the moles of gases on both sides are equivalent, nothing will happen if you increase the pressure or if you play around with the volume. Nothing will happen if moles of gas are the same on both sides. Now, adding a catalyst speeds up the overall reaction. It speeds up both the forward and backward rates by the same amount. Or more specifically, the forward and backward rates are scaled up by the same amount. And since the forward and backward rates at equilibrium are identical, that means that scaling both of them up by the same amount does nothing because they still cancel out. So for example, if you have 1 and 1, they cancel out. And if you scale 1 and 1 up to get 3 and 3, they still cancel out. So therefore, by adding a catalyst, the equilibrium constant is not impacted, and therefore, adding a catalyst does not impact a system at equilibrium. For a system not at equilibrium and trying to get to equilibrium by reacting, a catalyst simply speeds up the process by which the chemicals reach equilibrium and does not impact the concentrations at equilibrium. So it's not impacting the equilibrium constant or anything, and in the end, adding a catalyst simply speeds up the rate at which the process goes to equilibrium. So note that all of these assumptions hold true for your system, assuming that your system starts at equilibrium. If the substances are not at equilibrium, or in other words, the reaction is still going in a certain direction, and you start doing things to it while this is happening, then the reaction may or may not change directions. We need math to determine that, and that's in the next video. Now let's do a practice problem. We have a reaction, and we have the delta H of it. A system of NO2 and N2O4 at room temperature is in equilibrium. Some things are done to it to disturb the equilibrium. Predict the direction of the reaction if these disturbances occur. So what happens if we decrease the volume? Well, that increases pressure. So the reaction will favor the side with less gas. That is the right side, so the reaction will go forward. What about placing the system in liquid nitrogen, which has a boiling point of negative 195.8 degrees Celsius? So you can imagine this is super cool, and since you are having a very cold substance touching the system, then it will cool the system and decrease the temperature of this exothermic reaction. And if you're doing that, you're removing heat from the product side. And therefore, the reaction favors the products to restore the lost heat, and the reaction goes forwards. If you want to get more technical, then the forward reaction increases more than the backward reaction, so the reaction overall goes forward. Now, as I explained before, adding a catalyst will only increase the rate of the forward and backward reaction by the same factor. In the end, they are still equal, so they cancel out, so the system is still in equilibrium. Number 4, putting a gold ring, and assuming this gold ring does not affect the volume significantly, will not affect the equilibrium, since gold is not a part of our equilibrium expression. It is also a solid. And if you're wondering, here is the Kp of the reaction. Now, number 5, putting NO2 liquid at room temperature. So at first you're like, oh, it's a liquid. It won't work because it's a liquid, and that's not part of the equilibrium expression. Well, actually, at room temperature, this is the reaction, and we see that NO2 is clearly a gas at room temperature. But since we have some liquid NO2, that means it's going to evaporate or vaporize and return to a gas state at room temperature. And if you remember, gaseous NO2 is a reactant in the equilibrium expression, so the reactants will shift the reaction forward because the forward reaction will be faster than the backward reaction. Now over here we have some NO2, a reddish-brown gas, and N2O4, a colorless gas. Now I rewrote the reaction by flipped it around so that delta H was flipped from negative to positive, and heat is over here. And as you can see, if we increase the temperature, which is happening over here as we increase the temperature, heat is added to the reactant side, and there's excess heat. So the system wants to remove this heat, and to remove it, it won't go to the left because that's producing heat. Instead, it will move to the right because that's how it will remove this heat. And That's why when you increase the temperature, the reaction favors the product side and moves to the right. And that's why you see that as you increase temperature, the colorless gas is slowly converting into the reddish brown gas that we know is NO2. So that's all for now. Thanks for watching.